Hello everybody and welcome back to another AP Physics 2 video review. Today we are kicking it hot looking at heat transfer and calorimetry. So there are three main methods of heat transfer, and that includes conduction, which is primarily done in solids. So solid materials, and essentially what's happening here is if I have a block of material, solid piece of stuff, and I get one end of it hot. So now this end has a high temperature, TH for hot. And by definition, this side must be cooler. So we're going to call that T cold. What happens is the hot side is going to transfer its heat directly by conduction to the other side, causing this eventually to reach some T average in the middle overall. The way this happens is we got to think down on the molecular scale. So if we sort of zoom in onto the hot side over here, we have a bunch of, remember, a solid material is a lattice of molecules. So we have a bunch of molecules, and these guys are vibrating very fast because they are warmer, they have a larger kinetic energy. Remember that temperature is a measure of the average kinetic energy of the system. So on average, the guys on the left over here are moving much, much faster than the guys on the right. As these molecules move around, they are bumping into the less cool molecules. The hotter molecules are bumping into the less hot molecules, and they are transferring some of those energies in each collision. So high kinetic energy, we'll say KE high, collisions transfer this energy to molecules with less Ke. And so it sort of just moves down the line. These hot molecules are moving a lot. They bump into the slower ones. Now these ones are moving faster. They can transfer some of their energy to the ones over here. And eventually the ones on the left will have lost their kinetic energy. The ones on the right will have gained their kinetic energy. And eventually they're all moving at the same speed, not able to transfer any more energy either way. So eventually we reach equilibrium. When all molecules have same kinetic energy. Once they're all at the same temperature or same kinetic energy, they can no longer transfer it because, when they collide to each other, they have the same value as each other. They're not going to be able to transfer energy very well among each other. So that's conduction. Conduction happens directly in a solid material when high energy molecules bump into low energy molecules and they sort of trade their energy around. It's important to note that heat always flows from hot to cold, and so the heat transfer direction is always going to go from, say, in this diagram at least, left to right, from hot to cold. Our second method is convection. And this is going to be the primary method of heat transfer in liquids and gases. If I have a liquid and I heat it from the bottom, so we have T hot down on the bottom here, what's going to happen is these molecules towards the bottom of the container are going to be able to move more. They have more kinetic energy, and so they're able to move more readily up through the fluid, the rest of the fluid, and that's going to displace cooler molecules which have less energy, and they're going to sink down to the bottom. And so in convection, you sort of have this bulk transfer of motion. So you have the hotter material going one way, going up, for example. Heat rises, we say. We have the cooler material sinking down. And the heat is transferred in these sort of convective circuits or currents that form by this uneven heating. We have hot stuff down on the bottom. That's going to increase the energy. These molecules are going to be more readily able to move up through the fluid, and that's going to displace other molecules downward going the other way. And so this happens in ocean current cells. This happens in the atmosphere. We have convective cells that transfer air, from the ground where it's been heated by the sun up to higher up in the atmosphere. And in stars, there are very large convective cells due to the heat gradients there that allow material to be transferred around in that core. So convection is the prominent method in liquids and gases. Lastly is radiation. It's our third and final heat transfer mechanism. So conduction was number 1, convection was number 2, and radiation, we're going to end with number 3. Conduction works for solids, convection works for liquids and gases. Radiation, you do not need any medium for that heat transfer to happen, so no medium required. So for example, I have the sun. It is separated from the earth by a vast vacuum of space, but yet the heat that is produced in the sun, we have these energy produced in the nuclear reactions in the core. That heat is convected to the surface throughout the gas of the sun, and then it radiates through the vacuum of space to the earth. So typically, radiation occurs with an electromagnetic wave. Those are the ones that are able to traverse a vacuum. And radiation, you can sort of best describe it as a heat moves directly from one place to another. And these are not all mutually exclusive. In order to heat up the earth, you need both radiation and then convection, and maybe even conduction towards the end of it. So for example, radiation occurs when the sun emits its light towards the earth. It takes 8 minutes for that light to go from the sun to the earth, and eventually those radiated heat is going to hit the atmosphere. That extra heat in the atmosphere is now going to be able to convect through the atmosphere down towards the surface, or some of it might pass through the atmosphere and hit the ground. Once the ground has absorbed that heat, it can radiate it back out and then begin another convection cell from the ground up. Once that heat reaches your body, it's going to convect through your clothing or your skin, and you can feel that warmth that way. So heat transfer mechanisms can happen individually, or realistically, multiple variants are going to happen in order to get some end result. So you should be able to identify whether radiation, convection, or conduction is happening. And the simplest way to do that is really think about the most direct materials that are transferring the heat. If it's solid materials, that's going to be conduction. If you have a liquid or a gas, it's going to be a convection. If you just have a vacuum or no significant medium transferring that heat, it's going to be radiation. So that's the simplest way to identify the method of transfer. What materials is the heat being transferred through or from. All right, so we've identified these three methods of heat transfer. We're now going to focus mostly on solid materials for the rest of this, this review, and we're going to look at calorimetry, which is a way to sort of measure properties of a system or material based off how heat is transferred to or away from it. So we have this heat transfer equation. Q is our heat, is equal to M, what looks like MCAT, the famed medical test, or I guess test you use to get into medical school. Q is the heat for some reason. I don't know why. Usually it's a delta Q. It's a change in heat, either lost or gained from a material. M is the mass of the material. If you have more mass, you're going to need more heat to change your temperature. This value C here is known as the specific heat of the material. That is the amount of energy required per kilogram to change temperature by 1 Kelvin, which incidentally is also 1 Celsius. And T here is the change in temperature. So sort of breaking down this equation again, this is the amount of heat required to change an object's temperature by some amount. That is going to be directly proportional to how much stuff there is, how much mass is in the object. If there's more mass, you're going to need more heat to uniformly change that temperature. C is the specific heat. It is a value, material property of that object, and that is going to tell you how much heat you have to put in to change 1 kilogram or 1 mass unit of that material by 1 degree Kelvin or Celsius. So the higher this value, the more heat you need to put in. If we have two objects in contact with each other, they are going to transfer thermal energy between each other until they have reached equilibrium, aka the same temperature as each other. So two objects in thermal contact will transfer heat from hot to cold until they reach equal temperature. By conservation of energy, this is done by one object losing an amount of heat and the other object gaining that same amount of heat. So let's look at this mathematically. We have Q1 is equal to the negative, it's a delta Q, change in Q2. In other words, the heat gained is equal to the heat lost by the other object. If I have two materials, this is going to be C1, C2, and these could have different densities, so this could be M1, M2. This object starts out at a hotter temperature, TH. This one's going to start with a cooler temperature, TC. And this object is going to give away its heat until these end up at the same temperature. So the way that works is we plug in our MCAT on each side, M1, C1, delta T, final minus initial. This is the one that's going to lose the heat, so this one should be negative. and we have T final minus T hot. This is going to work out. The negative sign here assures that this term is going to be positive. If this one started out at a hotter temperature, then if I subtract that from the final temperature, this quantity here in parentheses will be negative, and the negative sign out front cancels that out to give us a positive value. So the amount of heat is a positive value. The negative sign just tells us sort of the direction that the heat is flowing. It's flowing out of the object into the other one. And the other one we have M2, C2, T final minus T cold. Because this is a colder object that's getting warmer, this final value minus the initial value will give us a positive value. So this positive number equals this positive number. That's a good sanity check to see if this makes sense. We want to solve for the final temperature. We can combine like terms. So I'm going to move the final temperature over to the other side here. And what we end up with is well, let's distribute plus M1 C1 TH So all I've done here is I've distributed the factors through, and I'm going to collect like terms. Let's make our T final positive. So we'll move this term over here and this one over here. So I get T final with the sums of the MC values. And over on the other side, this will also be positive. MC1, 2, TH plus M2, C2, TC. So the formula we're deriving here is completely general for a two-object system. Typically what you do when solving this out is you probably calculate the values out, so you just have a nice number and it's going to look a lot cleaner, but for the sake of having a cool equation we can derive. Let's finish this out. T final. Again, this is not an equation I would memorize. It's not an equation I would even save in my calculator. This is just sort of the end result. If you have, they have the same heat capacity, or if they have the same mass, there's going to be a lot of things that cancel out to make this thing a little more simple looking in the end. But this is the general formula. It's good to just sort of see from principles the heat lost equals the heat gained, how to actually figure out what the final temperature of this thing is going to be. Now, there are some tricks we can use. The temperature, sort of like, we can think about, we can estimate where the final temperature is going to be relative to the hot and cold temperatures based off the material properties. So, a larger mass or specific heat will tilt final temperature toward that value. In other words, if my cold object has a really large mass or a really large specific heat, then it's going to essentially, the hot one's going to radiate all of its energy and try to warm this cold thing up. And because it took so much energy to raise the temperature just a little bit, the temperature is going to end up more towards the cold side than the hot side. Lastly, if you have, that's essentially the main factor there. So if you have a larger mass or a larger specific heat, significantly greater than the other one, that's going to weight the final temperature more towards that boundary. So if we have T hot and T cold. If this M is much larger or this C is much larger, then the final temperature is going to be weighted more towards that. So that's more useful, I guess, in a multiple choice type question, which I guess there are going to be none, but it's still nice to have this rule of thumb at your belt for time purposes on the actual test. So that's a calorimetry problem. All you're doing is you're looking at heat gained equaled heat lost. The other more simple problem you can get with this is if you have like a water bath that's fixed. So I put a block of material in a large water bath, and there's just so much water here, there's so much mass that its temperature isn't going to change at all. So essentially what's going to happen is I'm going to put this really hot piece of material in this cool water bath, and based off, like, I know essentially that the block temperature will end up at the fixed water temperature. And based off the known mass, like this is how you actually measure the specific heat of an object, based off the measured heat that is transferred in this sort of reaction and the known mass of the block, and I know the change in temperature because I know how hot I heated the block up to. I know what fixed temperature the water is held at, so I know delta T. I can measure C from that. So experimentally, you can measure the heat produced by putting the block in the water. I know what the delta T is, I know the mass of the block, and I can figure out what C is. So possible lab design question they could give you, or a lab interpretation question is, maybe you you alter the mass of the block you put in, you look at the heat produced in that reaction measured, and then you can calculate the specific heat from the slope of that line. So maybe you have Y equals delta Q, you have X equals your mass. Different blocks might give you a different amount of heat produced, and then based off the constant value of delta T, your slope is going to equal T or delta TC, and you can calculate the specific heat from that sort of reaction there. Last thing is just sort of reviewing this equation for if I have two objects, they're not in direct contact with each other. So here's my cold reservoir of heat, here's my warm one, hot, and they're connected by some intermediate material. We can look at the rate of heat transferred in time based off the properties of this canal connecting the two reservoirs. So this canal has a length L. In other words, the two reservoirs are separated by some distance L. The sort of the canal has a width based off of its cross-sectional area A. So essentially this tunnel here, if it's wider, will allow more heat to flow through it. And then this, whatever this thing is made of, is going to have thermal properties K. And then again, the differential in temperature is also going to play a role here. If this is really hot and this is really cold, and that's a big, difference, and the heat is going to want to more readily travel between that difference. So QD, on the other side we have cattle. So this is the QD cattle equation. So hold so dear. If this material is better at transferring heat, K is the thermal conductivity. If it's better at conducting heat, it's going to transfer the heat faster. It's directly proportional. If the tunnel is wider, we have a larger cross-sectional area, we're going to get more heat transfer. So this is directly proportional. A is the cross-sectional area. That is also going to be directly proportional. If I have a larger tunnel, more heat can essentially fit through, so to speak, this tunnel. Delta T, heat differential. If the heat differential is very wide, then these very high energy molecules are going to definitely be able to transfer their energy over here more readily. If the difference is much closer, if this is 1 degree and this is half a degree, then the energy here is barely that above the other side, and so each collision is going to be less and less likely to transfer energy. If this is 100 and this is 1 degrees, then these ones are banging around really, really fast. They're almost certainly going to be able to transfer their energy to these lower energy molecules over here. So the larger the differential between the left and the right in this diagram, the more readily that heat's going to be able to transfer. But the further they are separated, clearly the longer it's going to take to get across. If these are really, really far apart, that heat has to actually physically go from here to here. It doesn't happen instantaneously, and the distance it travels is going to affect how long it takes for that heat to transfer. So the farther apart they are, the longer the journey and the harder it's going to be to get across. All right. We've talked everything about heat transfer, so that concludes today's talk. Stay happy, stay healthy, have a good one.